So now we're going to look at some problems on page 68. And the instructions at the top of the page say, if the technique chart states that you should use a particular MAS for a procedure at a specified distance and you must change the distance, what new MAS would be required at the new distance listed in the problems below. So what we're going to do is we're going to look at numbers 2, 4, and 6. And if you notice at the top of the page it says inverse square law worksheet. And you're sophomore students, and we've been through this, so you know that if we're maintaining density or we're maintaining exposure whenever we change distances, then that's not really the inverse square law. It's the direct square law because we're going to apply a new technique to a change in distance. And that is because of the inverse square law. It tells us that we reduce intensity as we increase distances. So the problem that we're going to work, or the way we're going to set this up, is not as the inverse square law, but in response to the inverse square law, we're going to use the direct square law. So if you were to take number 2 and set it up as the inverse square law, what you're going to see is that your intensity decreases. But remember, we're working the direct square law. Remember also that whenever we are working the direct square law, what we're going to be interested in is mass. What is our new mass? And whenever we're working inverse square law, most of the time that's going to be in MR or some sort of exposure, sieverts or rims or something besides mass. So mass is always going to be direct square law, and it's change in mass as opposed to change in radiation exposure. So on number 2, what we've got is mass 1 over mass 2 is equal to distance 1 over distance 2 squared. It's direct square law, mass 1, straight across from that is distance 1. So mass 1 over mass 2 is equal to distance 1 over distance 2. So your original mass was 240. Your original distance was 44. Your new mass is unknown. Your new distance is 40 inches. So you should set that up as 240 over x is equal to 44 over 40, and you square the whole thing on the opposite side. And what you should come to is, with the decrease, and this is how you know whether or not you worked it properly, with the decrease in distance, your mass should go down. So your technique should be right at 200 mass. It actually works out to be 198.347 mass. So if we look at number 4, we have an original distance of 30 inches with 75 mass, and we have a new distance is now 44 inches, and we don't know what our mass is. So we're going to set that up in the same way. It's going to be 35 over x is equal to 30 over 44, and square the whole second half of that. So by the time you cross multiply, you square it, cross multiply, and then divide out, what you should have is 161.33. Now you change it from 30 to 44 inches, you've got an increase in distance now. So again, you're calculating mass, you increase distance, your mass has to increase. If your mass decreased, then that should be your indication that what you did was you plugged it in wrong. You worked the inverse square law as opposed to the direct square law. And so number 6 is set up the same way. You got 320 mass at 60 inches. You're going to 72 inches. Naturally, you're going to need an increase in mass. So it's going to be 30 over x is equal to 60 over 72. Square all that, and what you should have is 460.8 mass. So if we flip over to page 69, what we see is on number 2, we have to calculate the mass before we can work the square law. So 50 MA at 1/4 of a second will give you 12.5 mass. So now you can set that problem up just like you did the previous problem. So it would be 36 over 30. Your original distance is 36. Your new distance is 30 inches. So again, you know that if you're decreasing distance, mass is going to have to decrease. So it will be 12.5 over x is equal to 36 over 30, and you square the second half of that. So what you should have, just to take it out one step further in the explanation, if you square 36 over 30, what you're going to have is 1296 over 900. So then you have 12.5x is equal to 1296 over 900. And if you cross multiply 12.5 times 900 and x times 1296, then divide it out from there. X would be 8.68 mass would be your new mass. Doing the same thing on number 4, what you would have is 6 over x is equal to 30 over 36. And by the time you cross multiply or square it, cross multiply, and divide it out, what you would have is 8.64 mass. Now, if you read the instructions at the top of page 71, it says for the following examples, determine the new radiation dose. Okay, stop right there. If you're talking about radiation dose, again, you're not talking about mass, you're talking about dose to the patient, dose to the image receptor. Now you're not going to be working the inverse square law. You're not going to be working the direct square law, you're going to be working the inverse square law. So looking at number 2, your original distance is 72 inches, your new distance is 60. So we're talking dose, that would be inverse square law. You got a reduction in distance, so your dose is going to increase. So your original radiation dose is 2.5. So what is your new dose? Your new dose is going to be an increase. So your distance went from 72 to 60. Your original radiation dose is 2.5. So you got 2.5 over x is equal to 60 over 72, and square the secondary half of that. And what you should wind up with is 3.6 mass. On number 4, you've got an increase in distance from 36 to 40, so you know your dose is going to go down. So you would set it up as your radiation dose is 25. You don't know what your new dose is, so it'd be 25 over x is equal to 40 over 36 squared. And by the time you square it, cross multiply and divide, then what you should wind up with is 20.25 is your new dose. And then number 6, you've got the same thing. You've got a increase in distance from 60 to 72. You increase distance, and what you have in an increase in distance is a reduction in dose. So 10 is our original dose. So 10 over x is equal to 72 over 60 squared. And what you should have there is 6.94. So remember, when we're talking dose, we're talking inverse square law. We're talking mass, we're talking direct square law. So those should be your hints. Your clue as to whether or not you work the problem properly is if we're talking inverse square law, an increase in distance is going to give you a decrease in dose. A decrease in distance is going to give you an increase in dose. If we're talking direct square law, an increase in distance is going to require an increase in mass. A decrease in distance is going to require a decrease in mass. Don't forget to square the second side of the equation. Don't forget to square the distances. Also remember that whenever you have a mass value, like on number 6 it was 6.94, most of your machines you're not going to be able to dial in that precise of a mass value. So if you get 7 mass, the question then becomes, is that going to make really any difference if the closest you can get to 6.94 is 7? And the answer is no. And I say that because what we need for a noticeable difference in our mass value is 30% change, right? So 6.94 4 times 0.3, which would be 30%, what we would have to have is a change in of mass of 2 mass off of almost 7 mass. So to see even a noticeable change, a noticeable difference between our actual mass value and our rounded mass value, what I'd have to have is almost a 9 mass, the nearest mass value to be almost 9 before it'd make any difference at all. So it doesn't really matter if you round mass up or down by a fraction of a mass. It's just not going to make any difference at all. So again, how much of a change does it take to see a visible difference with mass? And that would be 30%. So on each one of those that we looked at, if we rounded up or down to the nearest mass value, it really wouldn't matter. So is it critical to get the exact mass, or is it okay to round it? Absolutely, it's okay to round it. So now we're going to look at some word problems on page 91 and 92. At the top of the page on 91, it says using the 15% rule for changing KVP, fill in the missing information to produce a radiograph that has less contrast. Stop. So what we're talking about is 15% rule. 15% rule is density maintenance whenever we have a change in KVP. So if we change our KVP, we have to change our mass. What it's asking us to do is to have less contrast. Less contrast means longer grayscale, which means an increase in KVP. But we want to have the same density or the same exposure. So looking at our original technique on number 2, what we have is 600 MA, 0.02 seconds at 80 kVp. So we know we're going to have to increase our kVp. So 80 kVp times 1.15, because it's a 15% rule. So our new kVp should be 92 kVp. Now if you look, it's already given you the MA. So MAS being MA times time, really the only thing that you're having to calculate here is the seconds. And you shouldn't have to really put a calculator to this. If you had 0.02 seconds previously, then what you need is half of that, because you increased your KVP by 15%, you're going to reduce your mass by a factor of 2. You're going to cut your mass in half. It gave you the MA, so what you're going to do is you're going to reduce your time in half. So your new time would be 0.01. If we look at number 4, it's not asking us specifics, it's just asking us for overall mass value. So again, going back to our instructions, what we want is less contrast, so we need to increase our KVP. So our original KVP was 75. We're going to multiply that by 1.15, and that's going to give us 86.25 KVP. You've never worked with a machine that gave you fractional KVP, most likely, so 86.25, we can round down to 86. Calculate your mass. We have 800 times 0.035. That should give you 28 mass. So we're going to increase our KVP to 86, and that's going to give us an increase in exposure, but we want to maintain exposure. Cut your mass in half. Your mass should be 14. So now we're going to flip over to page 92, and we're going to look at problem number 4. So this is a full-on word problem all by itself. It says, what new mass and KVP are needed to produce a radiograph with less contrast? Stop there. You need less contrast, so what do you need? You need an increase in KVP. And half of the density of the original technique. And the original technique was 60 kVp, 400 MA, 0.07 seconds. So we got a couple of things that we've got to do with this one. What we've got to do is we've got to work the 15% rule to get us to kind of a baseline. So 60 kVp times 1.15, 60 times 1.15 gives us lower contrast, so that's 69 kVp. So our original mass was 400 times 0.07, and that gave us 28 mass. If we divide that in half, then that will give us 14 mass. But it's also asking us for a decrease in density. It's non-specific. Generally, whenever it's non-specific like that, a word problem, what they're looking for is half. So what you would do is cut your mass in half a second time, because again, when you increased your KVP and decreased your mass by a factor of 2, increased your KVP by 15% and decreased your mass by half, all you did was maintain the exposure. You need to decrease the exposure, so divide it again by 2, and what you should have is 7 mass. So your new technique should be 69 kVp at 7 mass. So building on what we looked at before, what if you needed an increase in contrast? Stop there. If you need an increase in contrast, what do you need to do? Decrease KVP. And an increase in density or an increase in exposure and a decrease in motion, and you change from 40 to 72 inches. So you got a lot of things going on here. So you need to take each one of those individually. So the problem is, what if you need an increase in contrast, an increase in density, a decrease in motion, and a change from 40 inches to 72 inches, where your original technique was 100 kVp, 100 MA, 0.1 seconds, and you need less time due to motion, more contrast, a 30% increase in exposure, and a distance change from 40 to 72 inches. So all you got to do is take it one step at a time. So the first thing that you would do is go back to your problem. It says you want to increase in contrast, so you need to decrease your KVP. So you decrease your KVP by 15%, then in order to maintain exposure, what you need to do is increase, because your original MA was 100, you're going to use the 200 MA station. So now you're back at the original exposure with better contrast or higher contrast. Now we're going to deal with the time issue. So you would increase your MA station from 200 to 400, and thereby allow you to decrease your exposure time to 0.05. So you've cut your time in half. So your new technique at this point is 85-20 mass. Now you need to increase your mass by 30%. So now your new technique is 85 kVp times 1.3 on the 20 mass would give you 26 mass. And then again, you're going to work your direct square law formula for the change from 40 to 72 inches. And what you're going to use is the calculation at 3.24. Whenever you go from 40 to 72 inches, your change in technique should be 3.24, roughly 3.25, and your new technique would be 85 at 84. Now, obviously, to keep your exposure time low, all of these changes would have to be changes to the MA station. The likelihood of finding MA stations that would fit directly into all that, very unlikely, but this is just an example, and don't get too hung up on that. This is just something that is used just for example. So in the unlikely event, some image receptor systems are faster than others, like CR is about half as fast as film or DR. So some algorithms, some computer algorithms are faster than others as well. So most of your CR systems are around 200 speed equivalent. DR is usually faster. Film, we had 200 speed systems and 400 speed systems. So what if we introduce, a lot of typos on this, what if we introduce an image receptor speed that is faster or slower than the other? So faster, what a faster image receptor system means is that it's more sensitive. So a 400 speed system is more sensitive to radiation exposure than a 200 speed by a factor of 2. So faster image receptor, the more sensitive they are, the less radiation dose that they need to achieve the same amount of equivalent exposure and image quality. So slower means the same thing. You need more radiation with a slower system than what you do with a faster system. So what you would do if we had this same problem here and we changed from a 200 speed system to a 400 speed system, then what we would need is half that mass. So let's take a look at it. If you needed an increase in contrast, an increase in exposure, a decrease in motion, and you change from 40 to 72 inches and use an image receptor speed that is twice as fast. So that's what we just walked through. It's everything that we calculated before, and it's just one more step, really. Fundamentally, it's no different than what we had before. The only thing that we're going to do now is to cut the mass in half, since the image receptor speed is twice as fast. So again, start by decreasing KVP. Now double the mass to get to the 200 speed by using MA, increase to 200 MA station. And that gave us the same exposure time and the same exposure. Now we're going to increase to 400, cutting the time back in half to 0.05, and it gave us, again, the 20 mass, 85 kVp at 20 mass. Now we're going to increase our mass by 30%, so we're going to multiply 20 by 1.3. That gave us 26 mass. We're going to multiply the mass now by 3.24 because we went from 40 to 72 inches, and our technique compensation for that change from 40 to 72 inches is 3.24. That gave us the 84 mass. But now we're going to use a image receptor speed that is twice as fast, so we need half the exposure. So we went from an equivalent 200 speed system to a 400 speed system. We went from CR to a DR system. We need half the exposure. So our new technique would be 85 at 42. So grids. Purpose for a grid is clean up scatter radiation and improve contrast. It absorbs scatter radiation that's scattered at a wider angle, so it doesn't really affect the Thompson or the classical scattering. It's all about the Comptons. So the things that affect scatter radiation are any kind of interaction. Most likely what we're going to get off of interaction is scatter radiation, some penetration, some absorption, and a lot of scatter radiation. So the grids are designed to absorb scatter radiation. The type of tissue that scatters most are soft tissues. That's why we use a grid for an abdomen, because primarily we're looking at soft tissue. Chest x-ray, we're primarily looking at lungs, so we don't necessarily need a grid. They say that it's even the heart, because of the increased OID of the heart, we've got a natural air gap, and you don't necessarily need a grid for a chest x-ray. Personally, I think the reason we don't necessarily need a grid for chest x-ray is because we've got natural high contrast structures. But okay, natural air gap, we'll go with that. So when should a grid be used? Anytime we're shooting an x-ray above 70 kVp, or if we're taking an x-ray of something that's 10 centimeters or larger. So shoulder size, knee size, or if we're using a kVp that's high enough to create a lot of scatter radiation. So increase kVp, increase soft tissue, increase scatter radiation. So what does it do for image quality? It improves the visibility. Not really so much sharpness of recorded detail, but the visibility of the recorded detail. You can shoot the perfect technique on a patient who's not moving without a grid, and you're going to cover up some of the sharpness of recorded detail with the scatter radiation. So the elements of a quality image is that you've got to have high contrast resolution and high spatial resolution. So you have to have both. Spatial resolution being sharpness of recorded detail, and contrast resolution being a visibility function. So it improves visibility, not sharpness. So what does it do to the image receptor exposure? It decreases it significantly, usually by factors of 3, 4, 5, and 6, depending on what your grid ratio is. If you have a low ratio grid, it could be a factor of 2. So anytime that you introduce a grid, you need to adjust your technique. So in adjusting the technique, the factor that we want to adjust is your mass. Again, because the things that affect scatter radiation are KVP and soft tissue. So naturally, if we increase KVP, we've got two things that go on. We create more scatter radiation, the grid has to work harder, and the grid does work harder, essentially. It's not an active thing, it's just that we created more scatter radiation, so there's more scatter radiation for the grid to absorb. If you remember when we were talking about grids in the spring, grid ratio or the Bucky factor changed with increased KVP. As KVP increases, the grid becomes more effective. So we want to increase mass rather than KVP. So it affects the image receptor exposure by decreasing the exposure to the image receptor. And what we want to do is we want to compensate with the increase in mass. Unfortunately, what that's going to do is increase patient dose significantly, again by 2, 3, 4, 5, even 6 times the radiation dose to the patient. So it improves image contrast by absorbing the scatter radiation that destroys image contrast. So technical factor would be mass, and we just talked about why we need to adjust that technical factor specifically. Dose goes up dramatically. So the two rules of thumb for using a grid we talked about, that would be 70 kVp or above, 10 centimeters or above. Incidentally, virtual grids, I don't think the software is quite to the point where virtual grids are nearly as effective as physical grids. To again review grid ratio and what it is, what we're looking at are two different things that we're comparing. It's a ratio. So it's the height of the grid strip divided by the distance in between them. Again, sometimes students have a tendency to make the height of the grid strip divided by the thickness of the grid strip, and that's not it. It's the height of the grid strip divided by the distance in between them. So an 8-to-1 grid would have a grid strip that is 8 times as high as the distance in between them. The higher the number, 8-to-1, 10-to-1, 12-to-1, the more mass you're going to need to compensate for changes in grid ratio. What that means is that the higher the grid ratio, the higher the dose for the patient. So the mathematical formula is grid ratio is equal to the height of the lead strip divided by the distance in between. Again, the purpose for the grid is to clean up scatter radiation. It improves image quality by increasing the visibility of recorded detail. Unfortunately, it decreases density or exposure, so we need to change our technique in response. It improves contrast, so it shortens the grayscale, gives us a higher contrast. We need to compensate by adjusting our mass. Patient dose goes up. Whenever we change grid ratio from a lower grid ratio to a higher grid ratio, we talked about all this already. So that's everything that we just talked about. Define grid ratio, formula for grid ratio. So when we change from one grid ratio to another, anytime that we increase grid ratio, so we go from a 5-to-1 grid to a 10-to-1 grid, what we're going to have to do is adjust our mass. And if we increase grid ratio, then go from a lower ratio grid to a higher ratio grid, we're going to need to increase our mass. Most of the time you're not going to do that. Most of the time you're going to change from no grid to the presence of a grid. But on the registry and in this class and on the test, you're going to have to change grid ratio. And if you look on page 99, you see grid conversion factors. And on this next quiz, you're going to have the Bucky factors, you're going to have grid conversion factors provided for you. So if you look on page 99, what you see is no grid, 5-to-1, 6-to-1, 8-to-1, 12-to-1, 16-to-1. Those numbers on the right-hand side represent the change in mass that you would need. So if you went from a no grid, which is a Bucky factor of 1, to a 5 to 1, you would need to double your mass. If you went from no grid to an 8 to 1, then you would need 4 times the mass. If you went from no grid to a 16 to 1, you would need 6 times the mass. That's what those numbers represent. There's a couple of different ways that you can perform this. Let's say you have a technique and you're changing from a 5 to 1 grid to an 8 to 1 grid. What you could do is divide your mass by the grid ratio that you're going from, and then multiply times the one you're going to. What I mean by that is, let's say you're shooting an abdomen with a technique of 20 mass. KVP really doesn't matter here. We're just changing mass. So what you would do is divide the 20 by, if you were using a 5 to 1 grid, you divide by 2. Using the factors, the grid conversion factors that you see on page 99, you divide by 2. 5 to 1 grid is 2. So you divide by 2, but you're going to an 8 to 1 grid, so what you would need to do is multiply that by 4. So if your original mass was 20 mass, 20 divided by 2 would get you to a baseline of 10 mass without a grid. And then if you multiply that by the new Bucky factor, 8 to 1, then you would have 40 mass. Your new grid ratio, or your new technique would be 40 mass at whatever KVP you had. But your textbooks give you this formula. New mass is equal to old mass times 2 over from. I find what I just described to be much easier, and you don't have to memorize a formula. So we're going to look at some problems on page 99. We're going to use grid ratios from page 99. We're going to look at some problems on page 202. So again, 2, 4, and 6. If we look at number 2, the problem is if a radiograph made using a 6 to 1 grid had to be repeated without a grid, what mass would be needed if the original mass was 15? So the original mass was 15. You don't really have to worry with the 2 over from. All you would have to do is divide the 15 by 3, and that would give you 5 mass. So number 4 gets a little bit dicier. If a radiograph is made using a 16 to 1 grid with 120 mass, what mass would be required or would be needed with a 12 to 1 grid? So you're reducing from a 16 to 1 grid to a 12 to 1 grid. So you're going from a high ratio to a lower ratio, still a relatively high ratio grid. Most of the grids you use are going to be 8 or 10 to 1. So it's going from a 16 to 1 to a 12 to 1 grid. So your grid ratio goes down. So since your grid ratio goes down, naturally your technique needs to go down as well. So 2 over from, what you have is 5 over 6 times 120 over 1. And what you should have is, remember, this is not a cross multiply type situation. This is just a direct multiplication. So it would be 5 times 120 would give you 600 divided by 6. Your new mass would be 100. Then if you look at number 6, if the technique for a radiograph made using a 12 to 1 grid required 60 mass, what mass would be needed if a 5 to 1 grid is used? Again, you're decreasing your grid ratio, you decrease the Bucky factor. You're going to utilize a lower mass value. So 2 over from, we've got 2 over 5 times 60 over 1. So 2 times 60 is 120 divided by 5. You should have 24 mass is your new mass. So now we're going to add grid ratio to the equation. So same problem that we had before. So the only thing that we're going to do is just add one more step to it. So if you needed an increase in contrast, an increase in density, a decrease in motion, and you changed from 40 to 72 inches, and you used an image receptor speed that's twice as fast, and you changed your grid ratio from 8 to 1 to no grid, which makes totally no sense at all because you wanted to increase your contrast, but whatever, humor me for the sake of this problem. Your original technique was 100 kVp, 100 MA, 0.1 seconds, needs less exposure time due to motion, more contrast, a 30% increase in exposure, and a change from 40 to 72 inches, and a change from 100 speed to 200 speed screen. What are you going to do now? Oh yes, and the change from 8:1 to no grid. So it's the same problem again, and now since we're going from an 8:1 to a no grid, and for our Bucky factor for the 8:1, according to our textbook here, is a factor of 4, then really all we have to do is take that one more step. So we would start by decreasing the KVP, double the MAS to maintain the exposure, but only by increasing the MA station. We would now cut our exposure time in half by doubling our MA, and we'd increase our overall mass by 30%, and we multiply our mass by 3.24 because we increased our distance, and according to the direct square law, we needed to increase our mass by 3.24 for a change from 40 to 72 inches. Now we're going to change our image receptor speed to twice as fast as what it originally was, so we're going to have to reduce our mass again, and then add in the grid conversion. So our new technique, after we ran through all that stuff before, our new technique would be, because our Bucky factor is 4, would be to divide 42 by 4, and that should give us 10.5 mass. So largely that was all about contrast, density, visibility factors. So now we're going to look at geometric factors. It is your image blur. It's going to be controlled by a number of different things. You want to utilize as low of an OID as possible, as practical of a SID as you can. That means if you're shooting a KUB on a patient, you're not going to be able to get 72 inches. So we got to settle. We got to remembering that SOD is a product of SID and OID. Naturally, if OID goes down, then your source to object distance would increase because your OID is decreased. Focal spot size, geometric unsharpness. So we've got focal spot size times OID over SOD. This right here is where people have a tendency to fall down. They don't calculate source to object distance properly. So source to object distance is from the x-ray tube to the object. So what you're going to have to do is do some calculation of SOD by your difference in OID and SID. So SID is equal to OID plus SOD. Where people have a tendency to fall down on this particular formula is an SOD. Remember, SID is equal to OID plus SOD. If you look on page 103, what you will see is some old terminology, most likely. OFD is object image distance now. OFD was object film distance previously. Your book may call source to object distance focus to object distance as well. So if you compare the calculations on 103 to 106, they're the same word problem. What you have is a 2.5 millimeter focal spot size. Your OID is 8 inches and the source to object distance is 32 inches. So your overall SID is 40 inches. So they're asking you about the geometric unsharpness of this image if we had a OID of 8 inches on a 40-inch SID whenever we have a 2.5 millimeter focal spot size. So it would be 2.5 times 8 over 32, so your geometric unsharpness would be 0.625. But if you flip over to page 106, what you see is as an increase in SID from 40 inches to 48 inches. And in that change from 40 to 48 inches, what we have now is a source to object distance of 40 inches. So in that change, what we're going to see is an improvement because we've got an increase in SID with the same OID. We've got an increase in SID. So our geometric unsharpness is going to improve. Now, your textbook may say x is equal to 1/2 or 0.05, and that's inaccurate. Textbooks can be wrong too. That should be 0.5. So it went from a geometric unsharpness of 0.625 to a geometric unsharpness of 0.5. So magnification unsharpness is controlled by the same things that we talked about before, with the exception of focal spot. It does nothing for magnification, but it does help with the unrelated sharpness. It doesn't matter how small of a focal spot you're going to use. The overall projected size of the image is not going to change with focal spot size. So in this case, what we're going to be comparing is object size over image size to SOD over SID. So where this differs from the big is to big is little is to little. If you remember, we had the bigs on one side and the littles on the other side. And in this case, what we're going to be comparing is image size divided into object size over SOD, or is comparing that to SOD over SID. So we're going to keep these two alike and these two alike. But again, if you invert the entire image, or invert the entire formula so that it's image size over object size is equal to SID over SOD, it's going to work out the same way. It's just a ratio problem. So where on the projected field size, what we're comparing or have on one side of the equation is this and that, and on the opposite side of the equation we had this and that. What we're going to have in magnification and sharpness are these two together and these two together. So now we're going to look at magnification formulas, and again we're going to look at on page 114 we're going to look at numbers 2 and 4, and we utilize this formula here. So number 2 says that let's see, determine the size of the projected image of an object that measures 3.5 inches if using a SID. That will be FFD as SID. Focal film distance and source to image distance are the same thing. 36 inches and a source to object distance of 30 inches. So you would set that up as 3.5 over x is equal to 30 over 36, and then you would cross multiply and divide it out, and the projected, so it'd be set up as 3.5 over x is equal to 30 over 36, cross multiply and divide out, you would have 4.2. Now if you flip back over to page 111, you see magnification factor. The magnification factor is calculated as sit over side. If we applied that formula to the same question, number 2, determine the size of the projected image of an object that measures 3.5 inches using SID of 36 inches and SOD of 30 inches, then what you've got is you've got a magnification factor. Your magnification factor would be 36 divided by 30, it'd be 1.2. If you applied that 1.2 to the 3.5 being your image size, your original image size, you're going to come up with exactly the same thing, 4.2. So you can use either formula. It just takes an extra step, and if you use magnification factor, you certainly don't want to forget to multiply your original object size by the magnification factor. So number 4, determine the size of the projected image of an object that measures 8 inches if using an SID of 48 inches and an SOD of 44 inches. So you'd set it up as 8 over x is equal to 44 over 48, cross multiply, divide by 44, and you should have 8.7. Again, if you worked it with the magnification factor set over side, you should get the exact same thing. In that case, it would be 48 over 44, and you divide that out, and what you're going to have is 48 divided by 44 is 1.09, and if you multiply that by your original image size or your object size, that would be 8. So your overall size again would be 8.72. Now specifically, number 5 is asking for magnification factor. So it's not really asking you what the size of the image is. So if it's just asking you for the magnification factor, then that's all the question is. If that's all the question is asking for, then that's all you give. Certainly doesn't hurt to give more information, but specifically you want to make sure that you give the actual magnification factor. So number 5 says determine the magnification factor if the SID is 40 inches and the SOD is 36 inches. So that'd be 40 divided by 36 would be a magnification factor of 1.1111 and so forth. So your projected size would be that times whatever your the size of your object is. Number 7, determine the magnification factor if SID is 60 inches and SOD is 54. So we have 60 divided by 54, again, is 1.11. Now sometimes you'll have questions that ask about percent of magnification. So remember, taking it back to calculation of percentage, 100% represents 1. So that's the whole of whatever you have. 1 represents the entirety of something. So this 1.11 indicates that we've got more than the whole, so that the projected image size is larger than the object size, and it's by 11%. 1.11 would be a 11% increase in image size over the object size. So whatever's past the decimal, if you have 1.1, then what you've got is a 10% increase. If you've got 1.2, if your magnification factor is 1.2, then you got a 20% increase. If your magnification factor is 2, then what you have is a 100% increase. If your magnification factor is 2.1, then you've got a 110% increase. That is your percentage of an increase in magnification.